Good day, I'm Dr. T and welcome to my office. Today I would like to talk to you about chemical formulas. Now to do this I first had to put the big disclaimer that chemical formula is actually a blanket term. There's quite a few different styles of chemical formula. We're only going to look at two of those today, but just keep in mind it could mean a lot of different things. So the two we're going to look at are going to be the empirical formula and the molecular formula. And their context depends on what type of compound you have. So let's first look at what we call molecules. Molecules are discrete clumps of atoms. And so I would want to know how many atoms of which type are in my molecule. And I could have just one type of atom, such as you find in sulfur. So elemental sulfur is a molecule. It's 8 sulfur atoms arranged in a ring, kind of like a little crown. So the way we represent this is the symbol for sulfur, a capital S, and then a subscript 8 coming after the end of it. So S8. Remember from the atomic symbols, the lower right-hand corner was left unused. Now we're going to use it. It indicates the number of that type of atom present. Now I should point out that when you're dealing with molecules, if you have 2 or more of a particular molecule, you indicate that with a full size number to the left of the symbol for the molecule. So if I was to say 2s8, that would mean I have a ring of sulfur atoms, 8 in the ring, and I have a second 8-membered ring of sulfur atoms. Likewise, I could say 2H, that would be 2 hydrogen atoms, or H2, that would be a pair of hydrogens forming one molecule. Of course, I can have more than one element in my molecule, water being a classic example. In that case, we simply just string them along. So I have H2, so I have a pair of hydrogens, and a single oxygen. We don't write the 1. If we put the elemental symbol there, then obviously there's at least 1, and kind of like music where we don't get redundant, if it's just 1, there's no reason to put a number there. Of course, this is why elemental symbols are going to have an uppercase letter to start with, and followed by a lowercase. That way you know that what you have is one element or 2 different ones, depending on the cases of the elements. There's no punctuation here. Okay, molecular formula, fairly straightforward. But not all compounds form discrete clumps. Many of them form what we call lattices. And this is alternating patterns of different elements. And you could have, say, a grain of salt, and that would be a billion or trillion or trillions of trillions, depending on how big this grain of salt is. Even a billion atoms is really tiny. Because atoms are really, really, really small. But you can imagine a trillion sodiums and a trillion chlorines. And how about a ratio? That might be more useful for us. And so that is what we use. The other chemical formula is known as an empirical formula. And empirical formulas are going to be a ratio of the atoms involved. So NaCl is a ratio of 1 sodium for every 1 chlorine. You're going to have a whole lot more than 1 sodium. You're going to have trillions and trillions and trillions of them, but it's a ratio. And these are always going to be the smallest whole number ratios we can use for the empirical formula. And before you ask, yes, you can do an empirical formula for a compound that forms molecules. And sometimes that's useful. But to be honest, if you've got a molecular formula, you typically use that with the compounds that form molecules. And your empirical formula, you tend to prefer to use that with compounds that don't, ones that form these repeating patterns called lattices. One last point, when you are doing chemical formulas, the order is kind of like grammar described thing. You know, in theory, OH2 would make sense, but no one would ever say that. Kind of like saying red big balloon. It just seems really wrong. It sounds like it should be big red balloon because, yeah, that's the way it goes. When it comes to chemical formulas, we typically write the atoms in the same order as you see them on the periodic table, with the ones on the lower left typically coming first, and then the ones on the upper right coming later. There are, of course, exceptions, especially when carbon's involved. if you have organic molecules, remember chemistry of carbons, organic chemistry, then that usually has a carbon first, hydrogen second, and then everybody else at the back end. But for the most part, unless you're dealing with those, it's basically the same order as you see on the periodic table. Now, I would like to point out that sometimes water will throw a curveball. Water is an interesting molecule, and it's small enough that it can interact with things kind of like a big atom, even though it's not, it's a molecule. And it does tend to like to interact with a lot of things. So quite often you will see for certain substances what we call hydrates, that when they crystallize, and typically they're going to be the lattice forming, but not always, when they crystallize, they will trap water in their crystal. This will actually be fairly important for us if we're trying to, say, weigh them out, and certain things like color may be affected by the presence of water. So in describing these, we will take their chemical formula like we would normally write, typically an empirical formula, put a dot after it, a pretty good size one usually, and then write a number, and then H2O. The number represents however many waters are trapped in the lattice of that particular hydrate. Now, if you have a hydrate, but you have removed the waters from it, you now have something that's known as anhydrous. And, of course, being not hydrous, meaning, wet or water. So something that you would typically expect to be interacting with water, that is not, is completely devoid of water, usually by cooking the thing, although there are other ways of doing it, is known as being anhydrous. Now, when working with anhydrous things, they typically have another term associated with them, and that is hydroscopic. And not everything that's anhydrous is hydroscopic, and not everything that's not anhydrous is not hydroscopic. Okay, what does this hydroscopic mean? This means that it really does like the water, and it is capable at normal conditions, so room temperature or thereabouts, of taking water out of the atmosphere. Sometimes this will simply be an anhydrous compound turning back into the hydrate, which can either be useful if we want to pull water out of the air, or downright annoying if we wanted the anhydrous one. You'll need to keep the lid on the anhydrous ones pretty good. Alternatively, though, there are some compounds which are so hydroscopic they can pull enough water out of the atmosphere to actually dissolve themselves in the water they have removed. So you can start out with a nice anhydrous crystal, and if you let it sit exposed to the atmosphere for long enough, and long enough is a surprisingly short period of time, you will end up with a concentrated solution in your container. Not a crystal, which is, shall we say, a tad bit annoying. So the take-home message here is make sure you put the lid back on before you're done, and keep track of who's doing what with water. With that said, have a wonderful day.